Welcome back to another video where we look at another diffusion problem. So according to the question, there's a 10 centimeter long uniform cross-section capillary which initially contains pure liquid H2O on the left and D2O on the right. These both liquids occupy the same amount of volume because H2O occupies the first 5 centimeters of the capillary, whereas D2O occupies the remaining 5 centimeters. And what we have is at t equals 0.1 second, the maximum molar diffusion flux was 2.78 moles per meter square per second, and pure deuterated water's molecular weight and density are 20 grams per mole and 1,110 kilograms per meter cube, respectively. So before we start solving the problem, let's look at this condition that has been given to us. So we have a 10 centimeter long capillary, and from 0 to 5 centimeters, we have pure water, H2O, and from 5 centimeter to 10 centimeter, we have D2O. So both of these liquids are separated, and they both occupy the same amount of volume. So that's the problem we have here. And let's assume that there's a barrier right down the middle, and it is removed at t equals 0 seconds. So after that, after like 0.1 second, we measured the maximum molar diffusion flux to be 2.78. And yeah, the molecular weight of D2O is given to be 20, and its density is 1110. So let's see what the first question wants us to do. It asks us, what is the overall mass flux corresponding to the maximum molar diffusion flux? So what that's asking is that at time t equals 0.1 second, what is the overall mass flux? So before we jump into the problem, I'd like to clarify one certain thing that's very important for this problem. So before we start doing the problem, it's important to make a distinction between two things. First, the mass concentration, and second being density. So first of all, what is density? So density is the amount of mass that is present in a certain amount of volume. So in this case, we're looking at a compound or a substance in isolation. It means that we have a 100% pure substance. It's occupying a certain volume, and if we divide its mass by the volume that it's occupying, we get its density. However, the mass concentration is more related to a mixture. So what that means is, for example, if we have a mixture of water and D2O, as in this case, if we divide the mass of water, only water, by the volume of the whole mixture, that's when we get the mass concentration. So that's how it's different from density. Density happens in isolation, whereas mass concentration is more related to mixtures. So yeah, so now since that's out of the way, let's calculate the overall mass flux of this at t equals 0.1 second. So the first thing that we know about the overall mass flux is that it is the product of the total mass concentration times the mass average velocity, which is written right here. So the question hasn't provided us with either one of these values. So what can we do? We can just calculate them. Then we know that the total mass concentration is equal to the mass concentration of water and the mass concentration of deuterated water, D2O. So let's calculate those values as well. So we know that the mass concentration of one component is equal to the mass of that component divided by the total volume that the mixture is occupying. So as we write it down, it's mass of water divided by the total volume of the capillary. I'm representing volume by this stylized V, so it doesn't get confused with these mass average velocities. So now we notice that we don't have either of these values either. So what we can do is we can write down the mass of water as the product of its density. I'm representing density by this row with a twiddle. And yeah, the mass of water is the product of its density times the volume that it's occupying in isolation. Not the volume of the entire capillary, but when the water is separated, say at time t equals 0, the volume that it's occupying and is what we need. So the total volume in isolation of water is only occupying this much. So we will multiply this volume by the standard density of water. So we get this expression right here. So what we know is that the volume that the water is initially occupying is only half of the volume of the entire capillary, the total volume. So we can write that down as the total volume being equal to 2 times the volume of water that it's initially occupying. So we write it down like this, and we notice that these two things cancel out, and what remains is that the mass concentration of water in the capillary is simply equal to its density divided by 2. So that's 1000 divided by 2, and we get the final value of 500 kilograms per meters cubed. That would be the mass concentration of water. In the same way, we calculate the mass concentration of D2O, which is its density divided by 2. So that's 1110. This value was provided by the question, and we divided by 2, and we get 555 kilograms per meters cubed. So now we have the first term that we need in order to calculate the overall mass flux of the mixture. So the total density is simply equal to the sum of the mass concentration of water and the mass concentration of D2O, which gives us the final value of 1055 kilograms per meters cubed. Now, we need to calculate the mass average velocity as well in order to get the overall mass flux. So we know that the mass average velocity is simply equal to the summation of the product of the mass fraction and the individual mass average velocity of that component. So in our situation, we only have 2 components, so that would simply be equal to the mass fraction of water times the mass average velocity of water plus the mass fraction of D2O times the mass average velocity of D2O. So first of all, let's calculate the mass fraction of these 2 components. So we know that the mass fraction of any component is simply equal to its mass concentration divided by the total mass concentration of the solution. So we know that we calculated that the mass concentration of H2O was 500, and we calculated that the total mass concentration of the solution was 1055, which gives us this value. In the same way, we calculate the mass fraction of D2O, which gives us 0.526. Now we need to calculate the individual mass average velocities of the 2 components. So the relationship that we have in order to calculate it is that the molar diffusion flux is equal to of a component is equal to the concentration of that component times the mass average velocity of that component. If we take the concentration to the other side, we get this equation. So in order to get the mass average velocity of a component, we know that we need the diffusion flux of that component and the molar concentration of that component. So yeah, in the previous video we discussed how the total diffusion flux in a closed system is actually equal to 0. And we also discussed that if it's a binary system, on top of that, the diffusion flux of one component is always going to be equal and opposite to the diffusion flux of the other component. So here we can say that diffusion flux of component A is equal to negative diffusion flux of component B. In this case, it would be water and D2O. So so the question has provided us with this value, the maximum molar diffusion flux, to be 2.8 moles per meter square per second. So we can say at t equals 0.1 second that if the diffusion flux of water is 2.8, then the diffusion flux of D2O is going to be negative 2.78. So yeah, we have the individual diffusion fluxes of the two components. Now we need to calculate the molar concentrations. So we know that the molar concentration of a substance is equal to its number of moles, which is represented by n bar, and divided by the total volume of the mixture. So now we go run into the same problem as we did before. We do not have any of these values. However, we know that the number of moles is actually equal to the mass divided by the molecular weight. We know the molecular weight of both water and D2O, but we still don't know the exact mass of those components. However, we already know that the mass of a substance is always equal to its density times the volume it is occupying in isolation, so which is the initial volume of the substance. Again, we know that the initial volume occupied by either water or D2O is actually half of the total volume of the capillary. So we can write this down again as the total volume being equal to 2 times the initial volume, and the initial volumes cancel out, and we're finally left with this expression, which means that the molar concentration of one component is equal to its density divided by 2 times its molecular weight. So we just plug that in for both water and D2O, and we end up with these values: 2.78 times 10 to the power 4 moles per meters cubed. Note that these two values aren't exactly equal. They're kind of unequal, but I didn't include all of the decimal numbers, so that's why they seem to be equal, but they're very close to being equal, but they're not exactly. So yeah, now that we have the individual molar concentrations of both the components, we can calculate the mass average velocity by the expression right here. We have both the diffusion fluxes and the molar concentrations. So simply putting on the values that we calculated, we get that the mass average velocity of water is 1.0008 times 10 to the negative 4 meters per second, and the mass average velocity of D2O is equal to negative 1.0018 times 10 to the power negative 4. The negative value here makes sense because in this situation, if water is being diffused in this direction, this z direction, let's assume that direction to be positive, then D2O needs to diffuse in this direction, which means it will have a negative velocity since the directions are opposite. So yeah, that's why the negative sign in the mass average velocity of D2O makes sense. Now, we have established that the velocity, mass average velocity, is equal to the sum of the mass fractions of a component times the mass average velocity of that component. So we plug in all the values that we've calculated, and we get the final value for the mass average velocity to be negative 5.26 times 10 to the negative 6 meters per second. Yeah, now that we have both the total mass concentration as well as the net mass average velocity, we finally calculate the overall mass flux, which is equal to negative 5.54 times 10 to the power negative 3 kilograms per meter squared per second. So yeah, that's the first part of the problem that we just solved. Now, the second question asks us to make an estimate for the order of magnitude for the maximum driving force for diffusion at time equals 0.1 second. So it's asking us to make an estimation for the driving force in terms of the order of magnitude that it will be in. So first of all, how do we calculate the driving force? We know from the book that the driving force can be calculated by this formula right here, which is equal to the summation of the mole fraction of component I times the diffusion flux of component J minus the mole fraction of component J times the diffusion flux of component I divided by the total mole concentration times the Stefan-Maxwell diffusion of component 1 in component I in component J. So in order to make the calculations easy, I'm just going to assume that H2O is component 1 and D2O is component 2. So let's calculate the driving force of H2O. This can be done using the driving force of D2O as well, because we'll find out that at the end both of the magnitudes will be the same. So for now, I'm just going to do it with H2O. So let's see, we have two components. So if we expand out this relationship right here, what we're going to get is the mole fraction of component 1 times the diffusion flux of component 1 minus mole fraction of component 1 times the diffusion flux of component 1 divided by the total mole concentration times the Stefan-Maxwell diffusion flux, diffusion constant of component 1 in component 1, and it goes a similar way in this part of the equation as well. What we realize here is that we have one component and the same component being subtracted from each other. So this whole term goes to 0, which is what's written here. And we end up with the relation, and we end up with this relationship. Now, we've already established that the diffusion flux of component 2, which is D2O, and the diffusion flux of component 1, which is H2O, is equal and opposite. So we can simply replace the diffusion flux of component 2 by negative diffusion flux of component 1. Likewise, we know that the sum of the mole fractions of all the components in a mixture is simply equal to 1. So what we can do here in a binary system is that the sum of mole fraction of component 1 and the mole fraction of component 2 is equal to 1, which can be written as this right there. So if we make if we make this replacement and this replacement into this relationship, what we end up with by doing some calculation is that the driving force is actually equal to the negative of the diffusion flux of component 1 divided by the total molar concentration times the Stefan-Maxwell diffusion coefficient of component 1 in component 2. So the good thing about this is that we already know what the diffusion flux of component 1, that is water, is. We've already calculated that. And the total concentration can simply be calculated using the relationship that it is the sum of the molar concentration of all the components in the mixture. So on top of that, we know that the Stefan-Maxwell diffusivity constant of component 1 and 2 is actually equal to the product of the thermodynamic factor times the diffusion coefficient. But one thing to keep in mind is that the mixture of H2O and D2O can be considered perfectly ideal. What that means is we can simply write down the thermodynamic factor, which accounts for the non-idealities, as being equal to 1. So what we get here is that the Stefan-Maxwell diffusion coefficient is simply equal to the diffusion coefficient. So one thing that we know about the diffusion coefficient is that it's always in the order of magnitude of 10 raised to the power of -9 if we're looking at a mixture of two liquids. So we can simply make this estimation into the main equation right here. So what we end up with after putting in all the values is that the driving force is almost equal to the negative of 2.78, which is the diffusion flux of water, divided by the total concentration, which we get by adding the molar concentrations of water and D2O, multiplied by the diffusion coefficient, which is in the order of magnitude of 10 to the -9. And this ends with the final answer of -5.0065 times 10 to the 4. So the question was asking us to estimate the order of magnitude of the driving force. And that is simply equal to 10 to the -4. So that would be the final answer for question 2. All right, let's take a look at the third and final question that we have for us today. So it's asking us to sketch the initial, which is at the time of 0.1 seconds, the intermediate at the time of 60 seconds, and the final at the time of infinity seconds of the mass transport profiles that are given in the textbook. So one thing to clarify here is that when it says t equals infinity seconds, what it basically means is that when the system has achieved equilibrium. So yeah, let's take a look at all the graphs that we're supposed to plot. Okay, the first thing we need to plot is the mass concentration of water and deuterated water. The second one would be the molar concentration of H2O and D2O. And then we have the molar diffusion flux of H2O and D2O. And finally, we have the average overall mass flux of the whole system. So, and we're plotting these with the position on the x-axis. So it would mean along the z-axis of the capillary. So yeah, along the z-axis of a capillary that I already mentioned before, it starts with a 0 right here and ends with a 10 here. Okay, so let's see what the graphs look like. First of all, in terms of the mass concentration of these two different compounds, in the initial phase, when time is equal to 0.1 seconds, these substances have not had the time required to mix around. So what's happening here is that for the most part, the concentration of H2O from 0 to 5 is pretty much constant at its density. And at the very 5 centimeter mark where the H2O and D2 are actually mixing, there's a very steep curve. What this tells us is that right at this mark, there's a very small amount of water molecules available. And as we go further ahead in the XZ direction, we see that there's even fewer amount of water molecules available. So that really lowers its density. And past the 5 centimeter mark, there's pretty much no water molecules at all. So the density of H2O is 0 there. So same thing for D2O. So from 0 to 5 centimeters, there's practically not a single molecule of D2O present. So its mass concentration is equal to 0 because obviously mass concentration is equal to the mass divided by the volume of the capillary. So it's pretty much 0 for this region. And again, close to the 5 centimeter mark, the two substances are mixing. That's why we see a very steep rise in the mass concentration of D2O. And then past the 5 centimeter mark, the mass concentration of D2O is pretty much constant at its density again. So looking at the final situation that we end up with, we can see that both the densities, the mass concentrations of H2O and D2O are constant, and they have been halved. So the reason they're constant is because the system has achieved equilibrium. However, the reason they're half is that the mass of the individual components, like the mass of water and the mass of D2O, has not changed. However, the total volume that they've been occupying has changed. It's gone from the 5 centimeters of the capillary to 10 centimeters of the capillary. So it means that the volume has doubled. However, the mass has remained the same. So since the mass concentration is inversely proportional to the volume, the mass concentrations will basically become halved for both the components, and that's why we have this situation when the system achieves equilibrium. The intermediate is basically the in-between of these two situations. So in after like 1 minute, the two components get a relatively sufficient amount of time to mix around. So on the far left side, there's still going to be a lot of water molecules, relatively high amount of water molecules with pretty much no D2O molecules, and same will be true for D2O, however, on the far right side. Towards the middle, there's a lot of mixing going around, so there's a less steep of a curve, a less steep of a slope. Now, moving on to the molar concentration of H2O and D2O, pretty much the same rules apply. For the most part, up to 5 centimeters, there's exclusively water molecules on the left side, and there's exclusively D2O molecules on the right side. There's a very steep curve, steep slope right down the middle, because that's where a very small amount of water and D2O molecules are mixing around, and that's why we see this steep curve. Same thing applies in the equilibrium situation as well. The molar concentration basically becomes halved because the total number of moles of each component stays exactly the same, whereas the volume gets doubled, which means the concentration has to get halved. So that's why we see this situation right here. Likewise, the intermediate is basically the in-between of these two cases, where a lot of the molecules are mixing around. However, there's still some molecules towards the extreme sides which have not been mixing. So that's why we see this curve with a rather gentle slope. So now the diffusion. One more thing about the molar concentration. We know that the standard molar concentration of water as well as D2O is actually 55,555. That's why there's this value at the top. And again, it gets halved when it reaches equilibrium. Now, moving on to the molar diffusion flux, what we see so in the question, it was provided to us that the maximum diffusion flux is 2.78, and we assigned that value to the water molecules, and we again established the fact that if the water molecules have a certain amount of molar flux, the molar flux of D2O is going to be equal in magnitude, however opposite in direction. So the diffusion flux is 2.78 at the 5 centimeter mark, because that's where the most amount of mixing is happening at 0.1 seconds, because that's where the contact is between the two substances. Likewise, the molar flux of D2O is going to be negative 2.78, again because it's equal and opposite. So the same rule applies to the molar flux as well, because for the most part, up to almost up to 5 centimeters, the two substances don't get a lot of time to mix around, so that's why we see this very steep curve. Moving on to the final equilibrium situation. At equilibrium, we know that things are not mixing around and they have become constant. That's why the molar flux is equal to 0 for both the components. Again, the intermediate situation is pretty much the in-between of the initial and final final condition. So the slope is a lot more gentle because a lot more of the molecules are mixing around. One thing to notice is that, of course, whatever the curve of the water molecule is for the diffusion flux will be mirrored by the D2O because equal and opposite in a closed binary system. Finally, moving on to the overall mass flux. So we see the steepest curve in the initial situation because that's when there is the highest tendency to mix around. That's when the masses are trying to spread or get diffused over the entire capillary. That's why at the very beginning we see the most amount of the steepest mass flux. And yeah, the maximum amount again was calculated to be negative 5.54 times 10 to the negative 3 kilograms per meter square per second. So in the final situation, again, when everything has achieved equilibrium, there's not going to be any mass flux because everything has mixed around. And just like in all the other cases, the intermediate is basically the in-between of these two situations where the mass flux has a lot more gentler curve and slope. So yeah, that was everything that we had to solve in this question. Thank you for sticking around for this long, and I hope you learned something today.